A trig identity is a trig equation. So it's a type of equation. It looks like an equation that is true for all permissible values of the variable. Okay? True for all permissible values. We use trig identities to simplify trig expressions and to solve equations. So once again, what I said at the beginning of this class is we're learning the identities because they're going to help us solve complex equations. Okay? You already know some simple identities. You've been working with these for years without knowing that they're identities. So let's look at two of these that you know very well. The quotient identities. How many people, show of hands, knew already that tan of theta is equal to sine of theta over cos of theta? I see everyone's hands going up because everyone knew that, right? So if cotan is the reciprocal of sine, then cotan equals cos over sine, right? We just flip them. And some people say too, like, don't ever forget also, no one's disputing this. Cotan equals 1 over tan, that's for sure. And tan equals 1 over cotan. But if you think of tan as being sine over cos, how did I can just flip these two. I can think of it as 1 over sine over cos, but that just becomes cos over sine, right? So for cotan and tan, you could also think of them, of course. No one is ever saying you can't think of them this way. Because sometimes that works for us, but sometimes we just want to work with sine and cos. So knowing that sine and cos is tan means that cos over sine is cotan. Okay? And I believe you already knew the reciprocal identities, right? So you already know two families of identities quite well. I think every single one of you, from my understanding and walking around talking to you, knew that sine was 1 over cosecant, cos was 1 over secant, and tan was 1 over cotan, right? Which is what I just wrote down here too. Cosecant is 1 over sine, right? Because I can just flip these two around. Secant, of course, is the reciprocal of cos, and cotan reciprocal of tan, right? Now, what you might not have ever put together is, if sine is 1 over cosecant, or 1 over cosecant is sine, if I multiply these two guys together, I'll get 1, right? That makes sense, right? That's just like saying, once again, when I say 3 equals 12 divided by 4, right? If I do a division and I get the quotient, if I multiply these two together, I'm going to get my numerator, right? So if sine equals 1 over cosecant, multiplying these two guys together should give me 1. And that should make sense to you, right? What am I multiplying together here? What are these guys called in relationship to each other? What are they? Not inverse, but starts with an R. Reciprocals, right? They're reciprocals of each other, correct? So give me a reciprocal fraction, or just give me a fraction. Any fraction. A half? Okay, what's the reciprocal of a half? 2 over 1, right? That's always going to equal 1, right? If I have like 17 over 21, the reciprocal is 21 over 17. It's always going to equal 1. Any reciprocal, any fraction multiplied by its reciprocal equals 1. So these are reciprocals, they'll multiply out to 1. That goes for any one of the reciprocal identities, right? Cosecant times sine equals 1. Secant times cos equals 1. And cotan times tan equals 1. Okay, that's going to come in handy too. This is what I'm saying when we explore the identities. This is true for any that I put in there. Let's just try this for a sec. Let's try secant and cosine. What's cosine of 45 degrees? 2 on 2? What's secant of 45 degrees? 2 over root 2, right? So secant of 45 times cos of 45 is always going to equal 1, right? Root 2 on 2 times 2 over root 2 always equals 1, okay? So an identity means I don't have to check for every single angle. I don't have to check for the 30s, the 60s, the 15s. I know that the secant of any angle multiplied by the cos of that same angle will always equal 1. That's what an identity means. Okay? So everyone's cool with these identities so far, agreed? Let's try looking at the Pythagorean identity. Here's another identity that you're familiar with. Okay? You've seen this before, right, when we started trig. Recall that point P on the terminal arm of an angle in standard position. Okay, so here's my angle in standard position. Initial arm, terminal arm, here's my angle, theta. Okay, has coordinates cos and sine. And remember why we can call them cos and sine? Because x, they actually started off as an xy coordinate, right? But x equals, or sorry, sine of theta equals opposite over hypotenuse, which will be y over 1. So sine is just going to equal y. Cos is x over 1, which just becomes x on the unit circle. Therefore, any point on the unit circle, instead of saying xy, I can think of them terms as the cos of the angle formed is equal to the x coordinate, the y of the angle of the, the sine of the angle formed is equal to the y coordinate, right? We've already heard that in the first part of trig. And it's just because the hypotenuse is 1. So this means x squared plus y squared is 1, correct? Now that's the equation of the unit circle, correct? Okay. Now if I just substitute my words cos and sine, that also means that cos squared plus sine squared would equal 1. Agreed? Okay, so that's what we call the Pythagorean identity. And I already went through once again in previous units, and I just did it now, why on the unit circle we can say that cos is equal to x, sine is equal to y, but that just means in terms of the angle, any angle, cos of any angle formed, cos squared plus sine squared equal 1. So that is the key identity here. Many, many identities arise from this key identity. So let's look at the 3 forms of this math statement. Like an identity is a super equation. Think of it that way. It's an equation, but it has superpowers because it's an equation that any angle will make this equation true. So it's true for all angles. So if we start with this key identity, cos squared plus sine squared is 1. First of all, I guess what I could do, I'm going to do something else here for you, because sometimes it's hard for students to make this leap. This also would mean, would you agree, that cos squared would equal 1 minus sine squared? That's true, right? And sine squared of the angle would equal 1 minus cos squared. Agreed? Okay. So how did I get this? How did I get this version from this? Any ideas? Not from the circle. It's actually from this equation. So we're just playing with this identity. There's no disputing that cos squared plus sine squared equals 1. Okay? So what if I take that cos squared plus sine squared equals 1, and what if I do this? What if I take cos squared plus sine squared equals 1, and now I'm going to play. If I divide every term, let's just divide every term by a sine squared. I'm allowed to do that in an equation as long as I treat every term the same, right? This is a sine squared, by the way. What if I just decided to divide every term by sine squared? It's keeping the equation true, it's keeping the balance. Well, what is cos squared divided by sine squared? That's cotan, right? Sine divided by sine is 1, and 1 over sine is cosecant, right? So I've developed another identity out of this key identity. So that's my second key identity. And of course, this can be moved around two other ways too, right? Cotan would equal cosecant minus 1, agreed? Like if I just isolated the cotan, cotan will equal cosecant minus 1, right? And what's the third form? I guess 1 equals cosecant minus cotan. Just remember, any one of these identities, once you have your three Pythagorean identities, you can manipulate them to isolate. They each have 3 terms, right? 2 trig functions in squared form and the number 1. They can be isolated to solve, or they can be manipulated to solve or to isolate each one of these. Kind of creating, not really creating 2 other identities, just manipulating in a different form. Now, how did this one happen? Well, if I took my cos squared plus sine squared equals 1, what did I divide it by this time? Cos, right? I mean, I can choose to divide by anything I want. I just choose cos and sine, or not me, but previous mathematicians, divided by cos and sine, because that's what we were given to work with, right? They're just kind of playing with these equations. So that's how we got the 1 plus tan equals secant. And then the other 2 forms would be what? I can isolate for tan. So tan also equals secant minus 1. Or I can just isolate the 1 and I get secant minus tan. Now you'll see that on your unit circle, these 3, they're not titled, or sorry, on your formula sheet, they're not titled on your formula sheet, but they're grouped in families. So this is your first set of identities. And these are called the Pythagorean identities. Now notice they don't give you the reciprocal or the quotient identities. They don't give you these guys on your formula sheet. They don't give you that sine is equal to 1 over cosecant. They don't give you tan equals sine over cos. And they don't give you that multiplying reciprocals give you 1. All of these are kind of regarded as general knowledge for grade 12 math students. At this point, you should know that tan equals sine over cos, right? So these guys you have to know. They give you these forms, but they don't give you the other 3 ways of writing them, right? But quite honestly, you could easily do that yourself, right? On test day, you could say, oh yeah, that means that this equals 1 minus cos squared, right? Hopefully you'll work so much with these that you won't really need to even write this out. You'll just know it almost instantly that sine squared plus cos squared is 1. So sine squared is 1 minus cos, or cos squared is 1 minus sine, etc. But you can easily manipulate these 3 guys around. Now, for the first week or so, we're just going to be using these 3 Pythagorean identities. We're not going to use these till a bit later. And also our general knowledge of the quotient and reciprocal functions. Okay? Now, these are called the Pythagorean identities because it comes from our triangle, right? Our x squared plus y squared equals 1 on the unit circle. That's why they're called the Pythagorean identities. They have squares in them, right? Because Pythagorean is side squared plus side squared equals hypotenuse squared, right? That's how it comes from. Okay, so just accepting what we just kind of played around with here and knowing you can always have your formula sheet in front of you. Hopefully by the break time, you'll sort of know what we're doing with this section a bit more. So let's talk about non-permissible values. You can see why non-permissible values happen because tan is equal to sine over cos. There's a fraction, right? Secant is 1 over cos. There's another fraction. So many of our trig identities are in fraction form, right? Almost, except for sine and cos, every single other one is an identity or a fraction, right? So there's going to be non-permissible values. So this is why we had to know all that previous stuff in trig. So many trig expressions involve fractions. Remember that the denominator cannot equal 0. The ratios tan, cotan, secant, and cosecant all have values of theta that can cause their overall value to be undefined. These values of theta are called the non-permissible values. Okay. So determine the non-permissible values for each expression. So we're using x's instead of thetas, but that could be a theta symbol for sure. I've got sine of x over cos of x. Okay? How do I state the non-permissible value? Well, sure, let's do degrees. But non-permissible value means, what am I saying here? Cos of x cannot equal 0. Okay? So where does that happen? Where does cos equal 0? 90 degrees and 270, right? Agreed? No. Cos equals 1 at 0 and 360. Right? Cos is x. So you really have to think of, yeah, so I think Carl's right. What does everyone else think?
Oh, yeah,
Yeah? So if we think in degrees, right? So my point is what, 0, 1, 1, 0, 0, -1, -1, 0. And cos is my first coordinate, right? Sine is the second. So I think Carl's, sorry, 1, 0. What am I doing? I did everything wrong. Okay? So cos is equal to 1 at 0 and 360. So cos is 0 at 90 and 270. So it's 9 degrees, 270. It didn't limit my domain. So I guess to answer the question fully, I guess I'd have to say x can't equal 90 degrees, x can't equal 270, and I probably should do this, and all coterminals, right? That just means 90, and every time I hit that same spot. And then you'd have to say k is an integer. Agreed? Okay, what about B? Non-permissible. Okay, so I start with this statement, right? Tan of x cannot equal 0. Okay, so that means x can't equal, there's usually 2 spots, usually, for every value, right, on the unit circle. So where does tan equal 0? Because tan is sine over cos, right? 0 over 1. That tan of 0 equals 0, right? And tan of 180 also equals 0. And then multiple, all the coterminals too, right? So that means, yeah, x can't equal 0 degrees. I always just do mine separately. It's just easier. So we're just, yeah.
If we use 90 degrees, it would be undivided, right? So
Pardon me?
if we use 90 degrees, tan 90 would be undivided, right?
Correct. Yeah.
So should we put it on
right, yeah. Yeah, let's do that too. You're right, Carl. Also, tan x is undefined at 90 degrees and 270, right? So how could we make this a little... I guess I'm going to have to just keep going down this way. I think there's a short way to do this, but I always just list mine. Sorry, you're right, Carl, because tan is undefined here. So tan can't be 0, and also this is just totally undefined, right? K is an integer. Now, the only reason we're doing this is to bring awareness to sometimes a trig statement is undefined, right? At certain values of x. So this statement could be part of an identity as long as we're aware that it doesn't hold true for when values of x are undefined for cos, right? So this could be, we could verify this statement for certain values of theta, but not all values of theta and not the values of 90 degrees or 270 or coterminals. They're just making you aware that identities are true statements, but there's still sometimes non-permissible values in an identity, just like there are for equations. Okay, how would I do the non-permissible value for this one? What do I have to be careful of? What's my opening statement? What can't equal 0? Well, first of all, 1 plus sine can't equal 0, right? So you're right, sine of x can't equal -1. Okay, so where does that happen? So x can't be then 270, right? So there's only one spot here. So 270 and then all coterminals. So that's how non-permissibles work for trig. So just keep in mind, we're going to kind of leave non-permissibles for today. I just want you to be aware that because identities involve so many fractions, trig ratios, that there are going to be certain values where the trig ratio is not defined, just like in all your other math work. Okay? And that's why it'll say, for some of your equations, for all permissible values, prove the following identity. That's just their way of saying, we know that there's some non-permissibles, so just be aware of those, but go ahead and prove the identity. Okay, let's try this one. Determine any non-permissible values, then write each expression in terms of a single trig function. Okay, I think I'm going to actually X this out. Let's not worry about the non-permissibles right now. We'll come back to non-permissibles, but I think you got the idea of why non-permissibles occur. Let's just do the second part. Write each expression in terms of a single trig function. Okay, so here we go. Here's our first start on identities. Single trig function means one trig function. So what do I see here? Cotan times sine. This expression, and this is an expression, just to backtrack to our vocabulary, the difference between an expression and an equation or identity is expressions don't have equal signs, right? The only thing you can do with an expression is simplify it. There's nothing to solve here, right? In order to solve something, I'd have to have an equals and like a left and a right hand side. Okay, so how do I go about simplifying this trig expression? I want to simplify it. That means make it smaller, cancel something out. Can anyone think of what I could do to cancel out? Yeah, I'm going to rewrite cotan as cos over sine. I'm going to leave sine, and then what happens? Cancel. And that helps me solve, simplify to one trig expression cos of x. That's how identities work. We're just playing with the relationships. Now, even though fractions cause problems, because fractions lead to non-permissible values that we also have to be aware of all the time, but fractions are a powerful thing, because you know what fractions allow you to do? If I can rewrite a trig expression in terms of a fraction, fractions always set you up to cancel things, right? Because you cancel from top to bottom, either top to bottom or diagonally top to bottom. So once you can rewrite with a fraction, usually you can do heavy duty canceling, right? So even though they're difficult in some respects because there's non-permissibles, they usually let you simplify. Okay, what about this one? I've got 3 trig functions, a secant, a cotan, and a sine squared. So secant times cotan times sine squared. Can I simplify this? Can I reduce it and do some canceling? Joanna says, yeah. What would you do, Joanna? What would you do first? Mm-hmm. Yeah, we just saw that one, right? And what would you do with the sine? Well, before I do that, just rewrite it, leave it. Why would I leave it, John? Yeah. So now I can do some heavy duty canceling, right? Cos. This sine cancels with one of these, so I'm left with just sine, right, Adam? I know I've only done 2 of these, but can you see kind of a pattern developing? What do you see here? What have you been noticing? There's more than one thing to notice. What do you notice? Rahel, have you ever done this before? Yeah? Who's brand new to this? Who's never done identities before? Dennis, do you notice anything from 1 and 2 that I did? Nothing?
You always go back to the 3
I'm kind of always going back to sine and cos, right? That's a strategy. That's a really good thought. Like, if you always turn things as much as you can. Now, as we go through identities, and in a couple of days we'll be doing bigger ones, tougher ones, that's not always the most effective way. But in identities, that is always one way that you can approach an identity. Just turn everything to sines and coses, right? Now, in the end, it might not always be the most efficient way, but it always will be a way that you can get your job done. Because it all comes back to sine and cos, right? Because how did our first identities were tan is equal to sine over cos, right? And what's your major Pythagorean identity that everything else sprouted from? Sine squared plus cos squared is 1. Everything comes back to sine and cos. So if you can convert everything to sines and coses, you usually can do what you're supposed to do. So let's try this one. Cotan times tan over cosecant. Now, the other thing that's kind of cool about identities is there's always more than one way to simplify an identity or to prove, right? So if I have 15 people in front of me, you could have started 15 different ways. Maybe not 15, but at least like 8 or 9 different ways, and then you all arrive at the same final answer. Okay? So, any thoughts about this guy? Who noticed that cotan times tan are reciprocals and equal 1? Yes. That would be the quickest way to do this one, right? These guys just equal 1. And then I get my 1 over cosecant, even if I just left it like that. And what is 1 over cosecant? It's just sine. Mm-hmm. Okay, how about the next one? Secant squared times cos all divided by cosecant. Did you do it, Eileen? Is it 10? I think it is 2. So how did you approach it? Eileen, do you want to, what did you do first? Or no, you can't describe it? John, what did you do?
The same is ended up with because it's I simplified it, so you do one of
Okay, so kind of, did you kind of separate secant squared to secant times secant? That's one thing I should say to you. I don't think maybe you picked that up over here, but I should say this. When we had x squared plus sine squared, another name for x on the unit circle is known as cos, right? So this was cos theta squared, right? Plus sine theta squared equals 1. In trig, we don't write it like that, even though that's technically what it is, cos theta squared. It becomes, the little squared symbol moves inside between the cos and the theta. So that's why it's written like this. So I should have mentioned that to you. It just looks strange in trig. So when I look over here, what this really is, it's 2 secants, right? It's secant x times cos x. That's what that means. All right, so that just means secant times secant. So this is 1, right? Is that what some of you did? So then you were left with secant over cosecant. And how did you get to tan from that? 1 over secant is cos, right? And this becomes sine? Is that what you did? Yeah? Is everyone okay with that, what I did there? So if I want to move a secant, where am I here? If I want to move a secant to the bottom, it just becomes cos, right? Moving secant, just switching places with these guys. If secant moves to the bottom, it becomes a cos, or if cos moves to the bottom, it becomes secant. So I just flip these guys. Secant becomes cos on the bottom, cosecant becomes sine on the top, and that's it. And it is tan. So awesome, well done. All right. So I'm going to give you something to work on now. And what we're doing right now is kind of just playing with identities, getting to learn the relationships. There's one key relationship besides your general sine is 1 over cosecant and tan is 1 over cotan, and that tan is sine over cos. But that stuff you knew already. The big one to remember is just sine squared plus cos squared equals 1. Right? That's a huge identity. What we're doing, why we're learning these, is once again because they are going to help us to solve tough trig equations. It's all about solving trig equations later on. And those trig equations are going to have stuff like this mixed in them, sines and coses and tans all jumbled around. Well, the only way we can really solve them effectively is to have them in terms of one trig relation, right? Like either just using sines or coses or just tans. So that's why we're playing with the trig identities. So I'm going to